Okay, welcome back. So, yesterday we ended with a discussion of the Stirling set numbers, which we defined. So the notation we use are these squiggle brackets here. Um, the These are defined as the number of ways to divide n objects into exactly k groups. These are called Stirling set numbers or Stirling numbers of the second kind. So, of course, we talked about Stirling cycle numbers yesterday, which were the Stirling numbers of the first kind. Here were some of the basic cases we considered, but the real action was here. So this was our discussion that uh, we get a recurrence relation similar to the recurrence relation we get for binomial coefficients and for the Stirling numbers of the first kind, that essentially generate the table or triangle of such numbers. And the way that we noticed this was noticing, again, thinking of this process in terms of one where someone is arriving late. So we need to form a configuration with n minus one people, so without that person, and then consider how they can be inserted into that configuration. So our way of doing this is we could divide the first n minus one people into k minus one groups, then place the last person into the kth group, a group by themselves. Or we can arrange the first n minus one people into k groups and then pick a group for the last person to join. This led us directly to, I enumerated both of those things. So in terms of the Stirling set numbers, this is the Stirling set number n minus one k minus one, and this second group is k times the Stirling set number n minus one k, because there are k groups to pick from here. So there are k ways to make that choice. And so combining those, because of this or here, which is our plus sign, combining those is exactly this recurrence relation, which generates that table that I linked yesterday. And so let's see an actual example of this before moving on to look at some nice identities that we get by considering generating functions involving these numbers, taking these numbers as sequence. So let's do an example where I'm asked to partition a set of four objects. So to partition the set containing four objects, A, B, C, D. So to partition this set into two subsets, we can place D in its own set. So if we do that, the option here looks like this. Or we can split ABC into two sets, then insert D into one of those sets. This is, so you can pause for a second if you need to see why what we just wrote out is exactly this recurrence relation. Okay. Now, if we do this, so the only way to put D into its own set really is this. Okay, what about this last possibility? So splitting this into two sets and then inserting D into one of those sets. So ABC, we could split that into two sets as AB in its own set and then C separate. But if we do that, we can insert D into the AB set or the C set. So this would be ABD, and then C is off on its own. Or we could do ABCD, So this is me splitting ABC into two sets, A, B, and C. In the first case, I put D in the AB set. In the second case, I put D in the C set. Okay. All right. Now I could have split ABC into the sets BC and put A on its own. In that case, I could put D into the BC set, or I could put D into the A set. And similarly, I could form ABC could be split into an AC set and putting B on its own. So I could insert D into the AC set, or I could insert D into the B set. Nope, nope, not a, so get rid of that. So this would yield 6 total configurations. But really, this is me. I'm trying to compute the Stirling set number 42 and finding that this is 2 times, because there's a choice of groups here, so I can put D into either of the two groups, D into either of the two groups, D into either of the two groups. So this would be 2 times the Stirling set number 32 plus the Stirling set number 31. The Stirling set number 32 is the number of ways to divide 3 elements into 2 sets. But again, that number of ways is just you're picking an element to be in its own set here, right? So you can choose A to be in its own set, B to be in its own set, or C to be in its own set. So there's 3 ways of doing that. So this would be 2 times 3 plus, what is the way of making one set exactly one subset from 3? There's only one way to do that, right? This is the one configuration that we get from inserting D in that case, because this ABC, that is the one single way to split 3 objects into a single subset, and so D gets its own set automatically. So there's 1. So this is 7. Okay, and we exactly used that recurrence relation. Okay, so as I said, that recurrence relation generates a table. Maybe I'll go ahead and put that table back on the screen. There it is. I mentioned yesterday that the right-hand column is the sum across the rows. For the Stirling cycle number, this sum across the rows was just n factorial. So summing across the rows, of course, is fixing in and summing across the k's. And that gives you this sequence of numbers that is denoted here by b sub n. Turns out these are the Bell numbers, and we're going to talk about those next after we've talked about these Stirling set numbers. But these are the sums across the rows in this triangle that we're generating with this recurrence relation. Okay, and look, you can see 7 right there, 7. Okay. Now, let us move to, so I'm going to say exercise 8 in this section. So exercise 8 in this section, which is on page 236. Uses the normal generating functions to obtain a relation on these Stirling set numbers with n fixed. But we can actually get something better if in the normal powers of x in the generating function we replace with the falling factorial powers. But we can obtain a better relation by replacing the ordinary powers of x with falling factorial powers. Okay. So, in this way, fix n and let f sub n of x be the falling factorial generating function, which we haven't defined yet. We're just giving it that loose name for the Stirling set numbers, where the power on this formal variable x here is the falling factorial power. Okay, so there it is. You can check that f naught of x is the constant 1, and if n is greater than or equal to 1, again, what direction am I heading in this way? What I want is to use this. This is why, as always, I'm peeling off the terms where this doesn't hold. It doesn't hold for the 0th term. But here we have this recurrence relation for all n greater than or equal to 1. And so, if n is greater than or equal to 1, I can use that recurrence relation. Using that, this is just rewriting it here. So this is a sum over k of the Stirling set number nk, x to the k falling. Plugging in my recurrence relation, this is a sum over k of, I'm just directly plugging in that recurrence relation. Let me bring it back. This is what I'm plugging in for my Stirling set numbers. And so this is k times the Stirling set number n minus 1k plus n minus the Stirling set number n minus 1k minus 1. And all of that is multiplying x to the k falling. Okay. Now, doing a little bit of rearrangement here, multiplying, like distributing this x to the k falling. This would be two sums, so sum over k of k times the Stirling set number n minus 1k times x to the k falling, plus the sum over k of the Stirling set number n minus 1. I can, so if I am going to do a tiny bit of re-indexing here, I could re-index this so that this is k, which would increment this to be x to the k plus 1 falling. Okay. Then I can pull off the x minus k term here in the next step. So now what is this? I can just copy this. This is the sum over k of k times Stirling set number n minus 1k, x to the k falling, plus this would be a sum over k of, I'm going to peel off the x minus k term in this product times Stirling set number n minus 1 k times x to the k falling. Okay. Now, the way that this has been written, I have this expression plus a sum where I have minus this expression. Minus k times all this. This is exactly what I have here. So those cancel. And I'm left with x times this expression. X doesn't depend on k, so that can be pulled out. Times the sum over k of the Stirling set number n minus 1k times x to the k falling. But this is this function except with n minus 1 plugged in here. Right? So this is simply x times f sub n minus 1 of x, which was, this is the thing I was manipulating this stuff to be. So you can use induction here, right? We have our base case, f of 0 of x is 1. Using induction, I can use this recursion to generate this formula for the ordinary powers. So x to the n is the sum over k of the Stirling set number nk times x to the k falling. And this is for n greater than or equal to 0. Why is this nice? What is this saying? Just like the Stirling cycle numbers allowed us to express ordinary powers as combinations of rising factorial powers, the Stirling set numbers allow us to express ordinary powers as linear combinations of falling factorial powers, where the Stirling set numbers are the coefficients. They're the weights in this these linear combinations. Okay. Recall, we actually had a similar sort of expression for the Stirling cycle numbers, but it was rising factorial powers instead of falling factorial powers. Okay. All right. So that's one useful fact. But in the beginning of this computation, we fixed n. So our sum was over k. What if we fix k and sum over n instead? So let's fix k. Fix k and consider the generating function for the Stirling set numbers nk, where we have fixed k. Well, this generating function, I'll write it as h sub k of x, can be written as a sum over n greater than or equal to 0. Why did I write k here? I meant n of the Stirling set numbers nk times x to the n. So this is just the standard generating function for that sequence. Again, you can check that in this case, h of 0 is equal to 1. Okay, so for k greater than or equal to 1, again, I want to use this recursion, but this h sub k of x Of course, this is the sum over n greater than or equal to 1 of Stirling set number nk x to the n. I am going to use my recurrence relation here, so I'm just plugging it in directly. This is the sum over n greater than or equal to 1 of k times Stirling set number n minus 1k plus Stirling set number n minus 1k minus 1, all that times x to the n. Just as before, I'm going to distribute this power of x so that I get two sums. I get the sum over n greater than or equal to 1 of k times Stirling set number n minus 1k times x to the n, plus the sum over n greater than or equal to 1 of Stirling set number n minus 1k minus 1 times x to the n. So then what is the idea here? In order to make this h sub k show up again here, I need to re-index these sums. I want them to start at 0. Okay, but how do I do that? Well, I could peel off an x here. Move this k outside. Remember, the sum is over n in this case, so this k doesn't depend on n. I can move a copy of x outside here, so this would be x to the n minus 1, but then re-index starting at 0, so this would still be x to the n. So I could have kx times the sum from over n greater than or equal to 0 of now re-indexing, having n minus 1 being replaced by n. Again, I've pulled a copy of x out here, so this became an x to the n minus 1. Then I replaced every instance of n minus 1 with n, which means that I have to start the sum at 0. So this is sum over n greater than or equal to 0 of Stirling set number nk now, x to the n. So that's where this n minus 1 went when I did the re-indexing trick. Okay, plus, same thing here. All I have to do is pull just a power of x out to do this. So this would be x times the sum over n greater than or equal to 0 of Stirling set number n k minus 1 times x to the n. Okay, and now I have what I'm looking for. I have the relation that I'm looking for. So this is k x times h sub k of x plus x times h sub k minus 1 of x. And so, using the fact that I have this equality, solving or simplifying this means that h sub k of x can be written as x over 1 minus kx times h sub k minus 1 of x. So this is what I get. Now, using induction, I can write this exactly as h sub k of x is x to the k over a product of terms. That product is 1 minus x, 1 minus 2x, and so on. So I have this rational function as my generating function. My idea is, as before, when we got a generating function that looked like this, we use partial fractions to decompose this. Okay, to put it in a form where we can more straightforwardly compare the coefficients that we're interested in and hopefully get some nice closed form expression that computes these Stirling set numbers. So I want to use partial fractions here. So using partial fractions here, what does that mean? So first, To make this partial fractions composition easier, so first we multiply by k factorial. That's just something that will make your life easier in this computation. So we start by multiplying by k factorial here. So when we do that, we seek coefficients in our partial fraction decomposition. We'll say a1, a2, and so on out to a sub k, such that this left-hand side, what's going to be our left-hand side is what h is. So this is going to be k factorial times x to the k over the product from m equals 1 to k of 1 minus mx. Notice this is exactly this h sub k multiplied by k factorial here. So k factorial x to the k times this product, 1 minus x, 1 minus 2x, and so on, all the way up to 1 minus kx. That's exactly this product, just using the product notation. Okay? So I seek coefficients such that this can be written as a sum of rational functions where each of these terms in the product are the denominators in each of those terms. Right? This is just general partial fractions decomposition notation. So this is what we're looking for. Okay. Now, let's clear denominators. So if we clear denominators here by multiplying through by this product, what do I get? I get that k factorial times x to the k must be equal to the sum from m equals 1 to k of the a sub m's times the products I use to clear denominators. So this would be the product from, I'm going to use another index here, j equals 1 to m minus 1 of 1 minus jx times the product from j equals m plus 1 to k of 1 minus jx. Okay, this is just multiplying by everything here to clear denominators entirely. Okay, so you might worry, like, oh, I need to get the most efficient common denominator I can. No, just clear the denominators. As long as you can always guarantee the denominators are clear just by multiplying both sides by everything in the denominator. Right, that moves things. Once we have this, now set x equal to 1 over m. If we do that, then what do I get here on the left-hand side? I have 1 over m to the k. So this is going to be k factorial over m to the k. And this is equal to a sub m times this product from j equals 1 to m minus 1 of 1 minus j over m times product from j equals m plus 1 to k of 1 minus j over m. Okay, so multiplying through by m to the k here, this tells me that k factorial is equal to, okay, let's see here. how many total copies of m do I get multiplying through here? I have m to the k minus 1 copies to distribute between the two sums, and I have a single copy of m left after that. So this is m a sub m times the product j equals 1 to m minus 1 of, I can distribute it to each term in this product, so that is going to be m minus j times the product from j equals m plus 1 to k. And this is why I don't get the total. I don't get all k. I only get k minus 1 because I'm missing the m term, and that's what I'm putting here. M minus j here. Okay. All right. So now this first thing I can write as m a sub m. What is this? This is like m minus 1 factorial. If you wrote this product out, this is like m minus 1 factorial. Times this product, j equals m plus 1 to k m minus j. But if I swap the order of this, instead of having m minus j here, if I have j minus m, I get a minus 1 for each product, each term in the product. I've done that. How many terms in the product are there? There's k minus m. So if I swap this order, I get a minus 1 to the k minus m coming out. M times m minus 1 factorial, of course, is m factorial. So I get minus 1 to the k minus m times m factorial a sub m times the product from j equals m plus 1 to k of j minus m, where I've swapped the order. And now that I've done that, this is actually just k minus m factorial. So this is minus 1 to the k minus m times m factorial times a sub m times k minus m factorial. So I have k factorial is equal to this. So what does that mean? That means a sub m is equal to, I'm just going to write this out exactly, minus 1 to the k minus m times k factorial over m factorial k minus m factorial. So this is minus 1 to the k minus m times the binomial coefficient, because that's exactly what this is, k choose m. So these are these coefficients in the partial fraction decomposition that I saw it. Okay. Thus, this generating function that I originally cared about, right? This thing, my h sub k of x, which is my generating function for these Stirling set numbers, okay, can be written now in terms of these, right? This generating function we found was exactly this thing. Well, we've multiplied by k factorial here. it was exactly this thing. So at the end, we can divide by k factorial. In fact, let's go ahead and just do that now so that we don't have to remember to do that later. So this is 1 over k factorial times that whole expression, like using this as my coefficient. So it is this thing. So my h sub k of x is then 1 over k factorial times the sum from m equals 1 to k of a sub m 1 over 1 minus mx. That is what I'm about to write. And it comes directly from this relation. Okay. Now, the point of this is that what is left behind, this is, of course, the term, the right-hand side in my geometric sum formula. So, this is 1 over k factorial times the sum from m equals 1 to k of minus 1 to the k minus m times the binomial coefficient k choose m times 1 over 1 minus mx. I want to use the geometric sum formula for this part so that this is 1 over k factorial times the sum from m equals 1 to k minus 1 to the k minus m times k choose m times the sum over n greater than or equal to 0 of mx to the n. All right, this is just me applying the geometric sum formula for that term. Okay. So regrouping now, x to the n, m to the n is what I get here, m to the n times x to the n. Rewriting this as a sum over something times x to the n. That's all I care about, is isolating the power or the coefficient on x to the n. This is the sum over n greater than or equal to 0 of 1 over k factorial times the sum from m equals 1 to k of minus 1 to the k minus m times k choose m times m to the n. All of this times x to the n. And this is what I've been looking for this whole time, because this is now the coefficient on the x to the n term. But this h is the generating function for my Stirling set numbers in k, right? Which means that whatever this is what's going on. The sequence that generates this generating function is, or has as its coefficient of the nth power of x here, is this Stirling set number in k. All right, so then comparing that, this thing that I've boxed is exactly the Stirling set number in k. And so the big thing that I wanted to show is a formula for computing the Stirling set numbers. So this is 1 over k factorial times the sum from m equals 0 to k of minus 1 to the k minus m, k choose m times m to the n. Okay, this is the formula that I get. So, for example, what about the Stirling set number 6,3? Well, this would be 1 over 3 factorial times the sum 3 times 1 to the 6th minus 3 times 2 to the 6th plus 1 times 3 to the 6th. And if you compute this, you will see that it is 90. Okay. So this formula is very, very nice, right? It might look cumbersome to you if you had to do this for very large numbers, but of course this sort of thing, very amenable to computation. This is a great tool for quickly figuring these out. And again, this just came directly. We had to do a lot of algebra to make all of this work out to get the result that we wanted, but ultimately, this again is just the power of generating functions and careful algebraic manipulation here to make everything work in the way that I wanted it to. So that is that for the Stirling set numbers for now. But as I mentioned previously, we had these numbers that showed up as the sums across the rows of this Stirling set number triangle. Sum across the rows. What is the sum across the rows computing? The sum across the rows, in the same way that the Stirling cycle number was the sum of permutations having any number of cycles, which was the total number of permutations, so it was n factorial in that sense. So that right-hand column wasn't very interesting for the Stirling cycle numbers. For the Stirling set numbers, this is how to divide a group of n objects, how to divide a set of n objects into any number of groups, right? Following those rules. So this is a more interesting thing here, right? It's maybe worthy of study on its own. Because, like I said, for the Stirling cycle numbers, this sum across the rows was just n factorial. It was just all the permutations. Here, this is the number of ways to divide a set of n objects into any number of groups, which is independently interesting for us. Okay, and so, to that end, let us define the following. So, these are called Bell numbers. So what do I want to define here? So the Bell number B sub n is the number of ways. So B sub n is the number of ways to divide n people into any number of groups. So here you are summing over the number of groups you're dividing people into until you get all possibilities. Right? Therefore, it is just the sum of the Stirling set numbers in K. I'm summing over K these Stirling set numbers. Okay. So, as I showed before, we can see the first few of those. Maybe I'll flash it on the screen one more time. Just one more time here. So this shows the values of these for n up to 8. You can see how this thing grows and what those numbers are. Okay. For n equals 4, see if you can cook those up on your own. There's only 15 such ways. See if you can actually enumerate those by hand. So here's our recurrence relation for Bell numbers. So remember our strategy for dealing with the Stirling cycle numbers and the Stirling set numbers, and if you go way back, even the binomial coefficients, way of dealing with this was to cook up a recurrence relation, then use generating function and that recurrence relation to get some kind of closed form expression that allowed us to crank out this count, to crank out a formula that just generated all of those numbers that we were interested in. So we seek, as before, a recurrence relation for these Bell numbers. How do we do that? So to divide n people into groups, we could consider the different ways to form a group containing one particular person, and then we have to choose some number k of the other n minus 1 people to join that person in one group and then divide the other people that remain into groups, right? So to divide n people into groups, we consider the different ways to form a group containing one particular person then we must choose some number k of the other n minus 1 people to go into the group with that person, right? Then divide the other n minus 1 minus k people into some number of groups. So this is like a dual take to our arriving late situation. So we didn't phrase it as someone arriving late, but rather we picked out like an individual's experience in this process. So pick a person that's going to be in a group. There are other people, right? I mean, maybe not. Maybe there's zero other people in the group with them, but in the sense that zero is an other person, there are other people in the group with them. So write your list of other people. That necessarily is some number of people from the remaining n minus 1 people, right? Once you've chosen all those people that are going to be in a group with that person, the remaining people are divided into some number of groups. The reason why we're fine leaving that general is because you see how we're building the recurrence relation, because the object we're interested in is counting the number of ways to divide n people in any other number of groups. And so now we have written it in terms of dividing some lesser amount of people into some number of groups. So thinking about it like this, what does this paragraph say? It says that building groups in this way says that these Bell numbers are actually the sum over k of n minus 1 choose k times the Bell number b sub n minus 1 minus k. Why? Because it's how many ways are there to choose k from the n minus 1 people, n minus 1 choose k, and then the number of ways to divide the remaining people into groups are this Bell number, the Bell number b sub n minus 1 minus k. Okay. Reindexing, right? Reindexing and using symmetry for the binomial coefficients. We get the following relation. B sub n is the sum over k of n minus 1 choose k times b sub k and this holds for n greater than or equal to 1. This is our recurrence relation. Okay. So this is our recurrence relation for the Bell numbers. Now, I want to use a generating function and this recurrence relation to come up with, ideally, a closed form expression for these things. So how do I do that? Well, it turns out that using a typical generating function won't really work. Using a typical generating function, in this case, doesn't give us what we want. So instead, we introduce a new type of generating function that we're going to call an exponential generating function. So we use an exponential generating function. What is that? What is an exponential generating function? So an exponential generating function for a sequence a sub n is the usual generating function for the sequence a sub n over n factorial. So quick example, if a sub n is the sequence c that's just constant, then the exponential generating function for this thing is the sum over n greater than or equal to 0 of c times x to the n over n factorial, because I use a sub n over n factorial instead, so I would get c over n factorial. I move the n factorial here just suggestively because, of course, this tells me that, oh, this is just c e to the x. Aha, this is where it gets its name. If you were wondering why is this called an exponential generating function, it's because if you apply it to a constant sequence, you get a constant times the exponential function, the usual exponential function. So, so this is the motivation here. Another example, of course, if a sub n is simply minus 1 to the n times n factorial, in this case, its exponential generating function, which you can check yourself, is actually just 1 over 1 plus x. Okay, you can verify that yourself. When you divide by n factorial, of course, this n factorial cancels out, so you just get an alternating sum here in these powers of x, and this is what you get. You get 1 over 1 minus minus x, right? So maybe here's the hint. That's what you get. So this is just a geometric series again, right? We know that the odd powers alternate in this geometric series. We plug in minus x instead, so that's what you get. Okay, and so we're still using a generating function. It's just we've slightly modified it in a way, and this can be more useful depending on the sequence in question. So our first example of us using this for a sequence are the sequence of Bell numbers. And so let E of x be the exponential generating function for the Bell numbers. So if that's the case, then this e of x is going to be the sum over n greater than or equal to 0 of b sub n over n factorial times x to the n. Okay, so differentiating. So we do term by term differentiation here. So using term by term differentiation here, taking the derivative here, I get n. So the only x showing up here is here. The derivative of x to the n, of course, is n times x to the n minus 1. N cancels with the first n from this product and leaves me with n minus 1 factorial here. So this would be, of course, the constant term in this expression when n is equal to 0. The derivative of a constant is 0, of course. So this sum starts at 1. So this is a sum starting at 1 of b sub n over n minus 1 factorial x to the n minus 1. Now I want to use this recurrence relation, right? This is always the thing I do. I have a recurrence relation. I put that into my generating function here. So b sub n, I replace that b sub n with this expression, which gives me this recurrence in the Bell numbers involving the binomial coefficient. So this is the sum starting at n equals 1 of 1 over n minus 1 factorial times, this is just me directly plugging in that recurrence relation, the sum over k of n minus 1 choose k times b sub k times x to the n minus 1. Okay. This is unpacking these two sums here. This is a sum starting at n equals 1, sum from k equals 0 to n minus 1 here because all the other terms are 0 in this expression. Actually writing out what this binomial coefficient is, multiplying it with 1 over n minus 1 factorial here, leaves me with b sub k over k factorial times n minus 1 minus k factorial, and all that is times x to the n minus 1. Okay. All right. Now, playing around with these sums a bit, this can be rewritten as sum over k non-negative sum with n greater than or equal to k plus 1 of this exact same expression. So this is b sub k over k factorial times n minus 1 minus k factorial times x to the n minus 1. Reindexing again here, summing over non-negative k and n, I can write this as the powers x to the n plus k, replacing every instance of, so we're re-indexing here, replacing every instance of k plus 1 with 0. So this would be n minus k plus 1, so this would be n minus 0. This would be n factorial here, and this would start at 0. So this would be the sum, k non-negative, n non-negative, b sub k over k factorial times n factorial times x to the n plus k. Okay. We can rewrite this, of course, in suggestive manner. So there's the sum over n greater than or equal to 0 of x to the n over n factorial. And in the k's, I distribute the x to the k's to the other part of the sum. So this is the sum, and k greater than or equal to 0 of b sub k over k factorial x to the k. And now you see what has been guiding my algebraic trickery, right? It's that I notice that if I group the things in this way, I am trying actively to group these in a way that e of x is showing up here. And I don't mean the exponential, although that's fine too, right? We're happy with that. But I mean the original thing I started with. That's always how these things worked. Whether we used partial fractions or whether we differentiated the power series once we got it and then compared terms and looked for this self-referential property, right? Look for it depending on itself here so that we could get this closed form expression. We did this for the Fibonacci sequence, for instance, right? This is our bread and butter when it comes to these generating functions. And so what is this? Well, this is just e to the x. And what is this? This is my exponential generating function of these Bell numbers. So this is e to the x times big E of x. Okay. And so what this means, if the derivative of big E is e to the x big E of x, this means, right, this is like a Calc 1 problem. This means that the natural log of big E of x, if I take that derivative, right, this is logarithmic differentiation here, this is going to be what? We use the product rule here, right? This is 1 over big E of x times E prime of x, which we just computed. So this is e to the x times big E of x divided by big E of x. So that is just e to the x. But if that's the case, integrating both sides here means that the natural log of big E of x is just e to the x plus a constant. Okay. But what is e of 0? E of 0 is the Bell number b of 0, which is 1. So this implies that that constant must equal minus 1. And so if the natural log of big E of x is e to the x minus 1, this means that big E of x is e to the e to the x minus 1. This is what we've been looking for because now we use the Maclaurin series for the exponential function. We need to do this twice because this is an exponential of an exponential. So we use the Maclaurin series for e to the x twice. We get big E of x is this is 1 over e e to the e of x, which is 1 over e times the sum over k greater than or equal to 0 of e to the x to the k over k factorial. And now I'm using the Maclaurin series for e to the x inside the Maclaurin series for e to the x. So this is 1 over e times the sum over k greater than or equal to 0 of, I can pull the k out here, 1 over k factorial, and then what remains would be the sum over n greater than or equal to 0. This is n, not k, of k x to the n over n factorial. Okay. Okay. Why the kx here? Well, because this can be rewritten, of course, as so that this is e to the kx. So it is like plugging kx into the Maclaurin series for e to the x here. So that's why I get this. Okay. But let's be careful here with how we do this algebra. Since we have a k to the n and an x to the n, let's separate those here. So this is 1 over e times the sum k greater than or equal to 0 of actually let's do this for n greater than or equal to 0 and put the other sum inside this. So put the sum for k greater than or equal to 0, k to the n, so we've peeled off this k to the n over k factorial, and then on the outside here I'm going to have x to the n over n factorial. And I have done this, I'm almost done here, so I'm going to rewrite this one more time. So this is the sum over n greater than or equal to 0 of 1 over e times the sum of k greater than or equal to 0, k to the n over k factorial times x to the n over n factorial. Because what we were looking for all along, going back to our definition of this expression, our e of x contains the Bell numbers here, right? There they are. Okay, and so these Bell numbers are what I actually care about. And so these Bell numbers then are the coefficients on the x to the n power in this, because of course, maybe I should write it like this, right? So n factorial times you write it like this, because you might complain that, well, this generating function, though, is not the generating function for the b sub n's, it's the generating function for b sub n over n factorial. So let's just write this out. So b sub n over n factorial is the coefficient on the x to the n power here in this expression, but that is exactly 1 over e times the sum k greater than or equal to 0, k to the n over k factorial times 1 over n factorial, right? Coming from here. And so comparing them without the n factorial, this means that my Bell number is 1 over e times the sum over k non-negative of k to the n over k factorial. This formula is sometimes called Dubinsky's formula. Sorry, spelled it. So this is Dubinsky's formula. And this gives us a formula for the Bell numbers. It's very nice. Right? This just directly, we can directly compute them in this way without directly referencing the Stirling set numbers. Okay. And remember what these things are counting. These are counting the number of ways to divide a set of n objects into any number of groups. Okay, so I think this is a good stopping point. I think in like the few minutes that remain, I don't have time to to introduce another topic sensibly, and these will be like the last 5 minutes of the course. So you get the last 5 minutes free. That's it pretty much. This is everything. So you've now throughout the course you've seen first half of the course, first 3 weeks of lectures. First half of the lectures were graph theory, sometimes involving combinatorial stuff, but mostly just graph theory. And then the last half was mostly combinatorics, so which hopefully has given you a nice, decent smattering of examples and things you can carry on going forward. So whenever you are given some graph theory or combinatorial sort of problem, you have had access to a wide array of the sorts of topics that can be used, or sorts of tools that can be used to attack those problems, whether it's combinatorially or in graph theory. Hopefully this will help you going forward whenever you never know when a question that you're working on, something seemingly completely unrelated, might eventually wind up being dependent in some way on a problem from graph theory or combinatorics that maybe seemingly has nothing to do with what you originally started out with, but hey, you translate it into one of these fields, and then you use techniques that maybe seem very off the wall to what you originally started doing, but once you have a solution to your problem, you don't care where it came from, right? So it doesn't matter what math went into solving your problem, you're just happy your problem's solved. So anyway, hopefully you've been exposed to a decent array of those types of tools and techniques. So if you